Welcome back. We have made it through the basics of R in the first 3 modules, and now we're ready to get into the fun stuff. So we are going to talk about programming in this video, and in addition to being fun, which I hope you'll agree at the end, programming is incredibly powerful. So basically, if you don't know a way to do something in R, you can code it up yourself with just some basic tools of programming, and that's what we're going to go through in today's lecture or video. We're going to talk about functions, building our own functions, building our own conditional statements, and iterating through multiple replicates of the same process over and over and over again. Basically, we're going to be able to learn to talk with computers and get them to do exactly what we want them to do using R. R is one of many programming languages out there, and R is specifically well suited to data science, but it's a programming language nonetheless. So what we're going to learn today is how to do basic programming tasks that you can do in any programming language, but we're going to work through them in R. And let's get started. So the first thing we do every time we start a new one of these modules is to save the script from this link here. So this is going to be script for the module 1.4. Just save it to your working directory. And then once you've saved it, just go to RStudio and load it up. So click on that folder icon and load up module 1.4. All right. We're first just going to clear the workspace so we have a fresh workspace to start with. So just run this line that just gets rid of everything in our global environment over here. And first, I just want to point out that objects in R can be one of 2 types. They can either be data objects like we've been working with, like vectors, data frames, lists, or they can be functions. So objects either store data or give us an ability to do things with data, manipulate data, perform analyses, do visualizations. That's what functions do. So functions do things on data that we want, and data objects store data. There's really just those 2 types of objects. You can see that in the global environment panel. Once we've loaded in some functions, you'll see that functions are categorized separately. So I can do that really quickly and just show that I can set a data object, a really simple data object, just storing 1 data point. But then I can also put a function in, and we'll go through how to specify functions. So B is going to be a function object that is just going to print hello, something like that. So I didn't run the function. Now we see that RStudio has already divided up our global environment into data objects here and functions here. It's not quite that simple, but essentially we can think of objects like that. And functions, we've already seen how important functions are. We've been using functions since the first module. We've seen functions for performing basic mathematical tasks, for doing plotting, for doing statistics. So we've been using them frequently, and we've noted that functions in general, or always, are called by the syntax, my function, and then parenthesis with any arguments that go into that function. So that's the general syntax for functions in R. We can write our own functions to perform tasks that may not be available to us in base R, and that's what we're going to talk about next. So to specify our own functions, we use the following syntax. So we say, we specify the name of the function that's going to be stored as an object in the global environment that can be called as a function. And we specify that that we're making a new function by using this argument or command called function. And then we put the parentheses and any arguments that function takes. Now this one isn't going to take any arguments, so we just leave it blank, but we still need the open close parenthesis. And then we add this curly bracket, which is going to enclose, so we have this big beginning and end curly bracket, and within those brackets, we're going to define what the function is going to do. All right, so basically the function is going to take in whatever's within the parenthesis, and here it's blank, so the function's going to take nothing. The user of this function doesn't have to supply the function with anything, but the function's still going to do something. So there's whatever it's going to do whenever it's called, it's going to do what's ever within the curly brackets. So let's get some practice just by doing this really basic function. So here we're making a function with no arguments, and within the function we're going to define this object that lives only within the function call. And that object's going to store a text string called hello world, and then it's going to return that text string. The return statement is a good thing to include within your function because it explicitly tells this function what it should return. So every time the function is called, what should it give us back? So it's going to take this input, it's going to do something, and it's going to return something. And that return statement only has any meaning within a function specification, and it tells us what we want back. So if we run this set of lines that define the function, and then we call the function, it returns the text string hello world. So it's not a very sophisticated function, but we're starting to get a hang of how it works to specify our own function. Now if we just type in the function call and don't put a parenthesis, R doesn't interpret it as that we want to evaluate that function. It just interprets it as print out what the function does, basically. So here we go. It just gives us the function specification right back. All right. And the same thing would happen if we tried to run our function B that we specified above without parentheses. It's just going to spit back the specification of the function. Now if we put parentheses, it'll run the function, it'll evaluate the function, it'll say hello. So we have a couple of really simple function calls. Let's do something a little more complicated. Let's specify a function that has an argument, and the argument is going to be a vector, and we're going to take this vector x, and we are going to compute the mean. Now R already has a function that computes the mean called mean, so this is redundant and not necessary that we specify our own function, so this is just for demonstration. But we're going to take the sum of that vector divided by the length of the vector and compute the mean within the function, and we're going to return that computed mean. One thing that gets a little confusing with functions is that any variable that is defined within a function is only defined within the function. So let's first run this and specify a random vector. So we'll just specify this vector we call foo, and then we'll use this function we just specified to compute the mean of that vector. And so the mean ends up being 5. Now I run that function, and you see that there's within that function, when I ran it, it created this object m. Now m never appears in my global environment. Even after I call the function, m only exists in the moment that the function is being evaluated, and then it just disappears. It only exists within the function call. So when we run this line, it takes this vector foo and it converts it temporarily into something called x, because we've given it this one input. And the input is a vector, and it has these values. whatever we give it as input becomes internally, just for that moment, for evaluating this function call, it becomes something called x. And now within the function, it defines this object m, and then it returns m, which is the mean of that vector. Once it does that, everything within the function, it doesn't matter anymore. All that matters is that the function returned the mean, and we can save that mean within our global environment if we save it as something. So this mean is defined as whatever that function returns, and now that becomes part of our global environment. So it gets a little confusing when you start to think about, you have complex functions and it's doing all sorts of things within the function. It doesn't matter really what's going on within the function. All that it matters is what the function ends up returning. None of the internal objects that are being specified end up in the global environment. It's all kind of in this other world, this other universe, the function universe that you're only calling, and once the function is finished evaluating, all of those become moot. They don't really exist anymore. Now the cool thing about functions is that we can give the function whatever we want as input. So we don't have to give it this vector for this mean function that we just wrote. We could specify our own vector. We could make a vector bar, whatever, that is a random set of numbers from a normal distribution. So I'll make a random set of 100 numbers with a mean of 40 and a standard deviation of 10. So now we have this long vector, and we can compute the mean of this. So let's see what the mean is. So my mean of bar. So we feed it this new vector. This new vector now becomes internally, temporarily, when the function is called, it becomes this thing called x. And then we compute the sum of x, and we divide it by the length of x, and we return the mean of x, whatever that is. And here, because we've put this vector now within our function call, that's the argument, that's what we're going to compute the mean of, it's going to compute the mean of that input, and that becomes 39.98, which is pretty darn close to the 40 that we specified, but it is random, so when you run it, it'd probably be a little bit different. All right, let's move on to another function. We'll just do this a bunch of times, and hopefully it'll get a little more, it'll make more sense the more you do it. So let's make a function that takes the square of any number. So we're going to feed it a number, and it'll give us the square of that number. Now, we could, x could be a vector too, so we could use this function to square lots of numbers. So let's run this. So again, this is really simple. It just gives one argument, and we square it. Now we can square a single value. Here we take 2 is the argument, and it squares it, so it becomes 4. We could square a vector too, and it'll square every element of the vector. And here we go. So now we're taking this vector of all the integers from 1 to 10, and we're taking the square of all of those. All right? Now, if we wanted to be even more fancy, we could give it another argument. So let's make a new function. Let's write this together. So this function is going to take any power of a vector. So we'll be able to specify, it's not just necessarily the second power, but we could take the third power, the fourth power. So we're going to add the power that we want to raise the numbers to as another argument to our function. So let's write this function. So this is any power, we'll call it. And this is going to be a function, and it's going to take x, which is a vector, or we can name it anything we want. A vector, and we're going to add a pow for power. So that's going to be, we're going to have two arguments to this function, and then we can use the curly brackets to specify the algorithm that the function is going to do every time the function is called. And within the curly brackets, we can write out the simple formula vector to raise, this is how you raise things to a power in R, use that caret, and then to the pow for power. So we've taken this input vector and we've raised it to the power of this other input, pow. All right. Now we could be really explicit here and use the return statement. So we could say return this thing, or we could save this as an internal function variable and say, result is this, and then you'd have to return the result. So if we want to be really explicit, we could do that. But by default in R, if you don't have a return statement in a function specification, it will return the last statement that is evaluated within the function specification. So in this case, it'll just return the result from doing that operation. And that's obviously a little bit easier and doesn't require as much typing. So that's kind of a shorthand. So if you don't see a return statement in some of these functions, that's the reason. You don't really need a return statement. But if you have a really complex function, sometimes it's really helpful to have that return statement in there. So it's useful to know about, even if it's not always necessary. All right, let's try running this any power function. So we're going to take any power, which is the name of the function, and use the foo vector that we specified, which is just a few numbers, whatever. And we're going to now take each of those to the third power using this any power function. Nope. We have to run that, and it takes all of the elements to the third power. All right, and we could do that with any power at this point. Use the 1.5 power if we want. All right, let's try another function. Let's build a function that that performs the Logit transformation of any probability value between 0 or 1 and converts it to the so-called Logit scale. All right, and we do this a lot in statistics because probabilities are obviously bounded at 0 and 1, right? If we Logit transform those probabilities, they are unbounded. So lower bound of negative infinity, upper bound of infinity, and that is a nice property for statistics. So oftentimes to do statistics on probabilities, we Logit transform first so that it has this nice property of being unbounded. All right, so the Logit transformation is just you take the ratio of the probability over 1 minus the probability, and then you take the natural log of that. So let's compute that. So in our terminology, this is the way we can do it. So the Logit is the name of the function, and we specify that it is a function, and within the curly brackets where the algorithm happens, we take the log of whatever the probability is divided by 1 minus the probability. So pretty simple. That's the Logit transformation. Now this is one example where there is no built-in Logit function in R, so it might actually be a useful thing for us to specify this function if we want to perform Logit transformations often. So let's specify this. Let's run this. So now we have a Logit function in our workspace, and we can use it. So let's compute the Logit of 0.9, and we could just compute the Logit of anything we'd like. Just call 0.0001, and we get a probability on the Logit scale. So a very, very low probability becomes very negative, a very, very high probability becomes very positive, and it's really unbound. I mean, it doesn't have any strict upper bound or lower bound. The higher the probability is, the closer it gets towards infinity, and the lower it is, the closer it gets towards negative infinity. All right. We can input a vector, so the x here doesn't have to be a single number or a scalar, it could be a vector. So let's specify a vector x and Logit transform it, and now we're storing the results from the Logit function that we just wrote as another object onto our workspace, and we can then print out what's in that object here. So we have specified a vector going from 0 to 1. So the Logit of 0 is negative infinity, as you might have guessed, and the Logit of 1 is infinity, and everything in between that has defined values. Since we have stored the results in our global environment, we can plot them out using the base plot function. So the x coordinates will be these x values that we computed the Logit for, the Logit transformation for. The y coordinates will be the Logit transformed probabilities, and we can use these plotting parameters to make the plot look a little better. We can give names to the x-axis and the y-axis and specify that we'd like to connect all the points together with lines so it looks all connected, and view this graphically, and we see the results that we take this bounded variable between 0 and 1 and convert it to something that's not bounded between 0 and 1. So that just illustrates what the Logit transformation is doing. Here's the probability scale, here's the Logit scale. So another way to visualize functions that is often convenient is to use the curve function in R. It's a convenience function for visualizing the results of functions and how functions can transform numbers. So here we're going to take the Logit function and we're going to plot it out from 0 to 1. So basically we're going to take all the numbers between 0 and 1 and apply this Logit function, and we're going to visualize it on a graph. And there we go. So the curve function is a really simple way to quickly visualize how a function transforms numbers. So we have numbers, you specify the lower bound and the upper bound of the numbers we want to look at and visualize, and then we have the function that transforms those numbers, and those transformations will be on the y-axis. So really simple and useful. So what if we want to do the opposite? What if we want to take some Logit transformed probabilities and convert them back to the probability scale? We can do that, and we can specify this function, and the function is just taking e to the Logit transformed probability divided by 1 plus e to the Logit transformed probability. So that's the operation that we need to do to back transform Logit transformed probabilities, and we can call this the x-bit or inverse Logit, and specify that function. All right. We can convert Logit transformed probabilities like 2.19, that becomes on the probability scale 0.9, and we can do that for any other number we want to do. So we can take -4, and that becomes a probability of basically 2%. So we can do that with a whole vector of Logit transformed numbers if we want. And I can't remember if I ran that. Yeah, so we ran that already. So that is a vector of Logit transformed probabilities. We can back transform them, and we get numbers mostly. So negative infinity becomes 0. Infinity becomes not a number. That's interesting. Not sure exactly why negative infinity works, but infinity doesn't. I'm not going to think too hard about that right now. So let's take these Logit transformed probabilities and convert them back to probability scale. We can save the results as this xpit logit x. So we've logit transformed and then we've back transformed. And let's look at what that looks like again. And we can compare that to our original x values, which looks pretty similar because it should, because we've basically taken these probabilities, transformed them to logit, and then back transformed them back to the original probabilities. So if we plot x versus this transformed and back transformed version of x, we should see a one-to-one line, which we do. And finally, if we plot out a set of Logit transformed probabilities going from -3 to 3, and then we, on the y-axis, plot out the back transformed probabilities, so back to the probability scale, we get the classic logistic curve, kind of S-shaped curve. So on the x-axis, we have this unbounded Logit transformed scale from -3 to 3, and here on the y-axis, we have a bounded transformation that ends up being a probability scale where 0 is the minimum and 1 is the maximum. All right, the last function we will create is a function that takes two arguments. It takes the number of animals being monitored, so imagine we're monitoring a wildlife population, and N is the number of animals being monitored, and D is the number of animals that died. So we can imagine we've put radio transmitters on a bunch of animals, and after 1 year, we go out there, we track all the animals down and figure out which ones are still alive, which ones are dead. And so D is the number dead, N is the total number monitored, and we're going to build a function that just computes the mortality or computes survival from these data. So we're going to take the total number of survivors, which is the number monitored minus the number that died, divided by the total number being monitored, and that's our survival rate, say for a 1 year period. So let's read that function in, and we can, for total number monitored of 10 and a number that died at 5, we should compute a survival rate of 50%, and that's what it does. We could imagine that we're simulating a whole research study, and we can sample the number that died over a total of, say, 10 years, and the number that died is going to be sampled randomly between 0 and 50. All right, so we're going to sample 10 numbers between 0 and 50, and we're going to say replace equals true, so the same value could come up multiple times, and it's going to look something like this. So we have 10 numbers between 0 and 50 that we have just randomly sampled. Yours is going to look a little different because it's a random sample. And the total number monitored, let's say we always monitor 100 individuals every year, so it's just we're going to repeat the number 100 10 times for 10 years, so N should look like this, with just 10 100s. And then we can take those two vectors, total number monitored, total number died each year, and compute the survival every year. All right? And finally, before we move on to conditional statements, let's plot this out. So we're going to plot, the x-axis is going to be year, and the y-axis is going to be survival rate. So we'll take year 1 to 10 on the x-axis, the survival rate we just computed on the y-axis, and add some graphical parameters. And here we go. It looks something like this. Yours is going to look different because it's random. All right, hopefully function specification makes a little more sense now. I would totally recommend playing around with building your own functions and making sure that this makes sense to you. And if you do have any questions, please let me know. All right, the next programming task or concept I'd like to go over is the conditional statement, which is kind of a fork where you say, if one thing is true, then do this. If it's not true, then do something else. And now we can start to get quite complicated quickly using conditional logic gates. And so it can look kind of like a tree where you have, a test. And if it's true, then we do another test. And if that's true, we do something. If that's false, we do something else. So, and if that test is false, we do another test, and so on and so forth. So we can get quite complex quite quickly using simple logical statements. Let's go through how we can do this in R. So first, let's just imagine we are wildlife biologists, which I keep coming back to because I am one. And we're going to be looking at detection probability, and imagine we're going out in the field and there's a certain probability of detecting or not detecting each individual that we're monitoring, and we can assign a probability of detection, and we can simulate whether we are or are not going to see this individual when we go out in the field and look. So we're using the random binomial generator, and we're going to generate one random binomial. So basically we're simulating a single time going out in the field, and we either detect or don't detect this individual. So we're just going to simulate one random number, and it's going to be either 0 or 1 because there's only one coin flip essentially in this trial, and the probability is p, which we defined as 0.7. So essentially you can imagine a single coin flip with a probability of success equal to 0.7 in this case. So let's run that, and it will be either 0 or 1. It's random, so you might get something different, but I get a 1 here. And if I want to if the x ends up being 0, it's going to be not detected. So basically, I'm going to do this test. So if this x in my case is 1, if it's greater than 0, in which case, I could just say if x equals 1, print detected. Otherwise, print not detected. So I'm going to give a description of the results. In this case, since I got a 1, it's detected. But if I run this again and I get a 0, that was kind of lucky. I just got a 0. Didn't have to be that way, but now if I rerun this, it says not detected because x is not equal to 1. So then it evaluates whatever we put in this else statement. So that's generally the syntax for if then else in R. It basically goes if some test, some Boolean test, so so that test has to evaluate to either true or false. So if some test, then in curly brackets we do something if true, and then we say else, and then we add the curly brackets again, and whatever we specify what we want to happen if do this if false. And we can build more complex conditional logical statements if we add another test. So else, we could say else if another test and then say do this if other test is true, and then we can add another else statement that's going to catch all the falses that don't pass either test, and do this if both tests are false. So that's the general syntax. Of course, RStudio is not liking this because this isn't actual R code. This is kind of pseudocode. So if I want to comment this out, I can just Control-Shift-C, which is a shortcut for commenting out a whole block. And that way, RStudio is not going to throw warnings at us that this is not legitimate R code. All right. So we can combine conditional logic with functions, and we'll do that in the next this next section here. We're going to make the Logit function, which we already did. So we have a function called Logit, which just takes something on the probability scale, transforms it to the Logit scale. But let's look at what happens, because the Logit function really is only defined for inputs between 0 and 1, like probabilities. What if the function is given a different input? So we give the Logit function an input of -0.1 and run it. It gives us this NaN result, which means not a number. It basically means the mathematics doesn't work out here. There's no legitimate result here. And we might not want that. We might not want to see that warning. In fact, we might want to include a more informative error message. So we might want to do some sort of a conditional test. Is the input between 0 and 1? If not, we might want to submit an error and give the user not just a warning, but an error that says that, look, you can't do this operation for values outside that interval between 0 and 1. So we can do a test and use a conditional statement within the function. So let's make a safe version. We're going to call it logit.safe, a safe version of the Logit function. And let's see what we do inside this function. So first, we're going to give a vector of probabilities, ideally between 0 and 1. But if the probability is not, we're going to throw an error in this case. So first, we're going to do a test here. So one way to debug into a function and sort of test to make sure we know what's going on is to assign that input, in this case x, to be an actual vector. So let's make a vector with one bad value and a couple good values, 0.1, 0.5. All right, so now we're going to do a test, and we're going to use this Boolean logic. So first we're going to take this x is less than 0, and this other Boolean test, x is greater than 1. And these are both indicating bad conditions. Either if x is less than 0, the Logit operation is not going to work. If x is greater than 1, the Logit operation is not going to work. So if either of these things are true, so we're going to use the OR operator here. If either of these things are true, then the observation is bad. Like that vector element is not a good, it's not going to be appropriate for running the Logit function. So in this case, this correctly identifies the first element as bad. So we're going to save this internally within the function as this vector of Boolean true and false values that is called bad. And next we're going to use this other Boolean statement called any. So any is going to take a vector of trues and falses, and if any of those elements are true, it's going to return true. So in this case, it should return true. And now we're going to put that in an if statement. So if this test is true, then we're going to throw an error message. So this stop command is telling R to stop everything and throw an error, and the error is going to have this is going to be the error that it gives if one of the elements is inappropriate, if it's not within 0 and 1. So if you run that, you'll see that it throws an error, and it'll happen if we run the function if this vector x, this input to the function, if any of the vector elements are outside that range. Otherwise, use the else statement. Otherwise, we will do the correct thing and compute the Logit transformation. All right. So let's run that. And just a quick overview of what I did by specifying this x vector. I was able to go into the function and just sort of go through this algorithm and make sure everything works. And that's kind of a useful thing to know how to do. If you're not sure, what's going on within the function, sometimes you have a lot of different commands that are included within the function. It gets pretty complicated. And if any one of those is not right, then the function is not going to work appropriately. So if you can test it line by line as you write the function, it's really useful. So all you have to do that is to specify whatever that function expects as input. Specify that within your global environment, and then you can work through it. So if there's something called x in your global environment here, then you're able to run this line. And that's essentially what R is doing when you call the function. It's just, temporarily, while the function is active, while it's being evaluated, whatever you give it as input is going to be called x, and then it's going to run these lines. So what you're essentially doing is doing what R does when you call that function. You're just giving this input some values and evaluating, going line by line and running each of these commands and returning whatever the last thing is that function algorithm does. So in this case, it's going to return this, or it's going to throw an error. It's going to correctly return the Logit transformation of the probabilities, or it's going to throw an error. So let's run that, and we'll specify a vector. In this case, a sequence that goes from -1 all the way to 2 in units of 0.1, and clearly some of these are well outside the range of 0 to 1. So we're going to run into some problems if we try to do Logit transformation here. Let's uncomment this so we can try the two different Logit functions. So if we run the Logit transformation as we specified earlier, we'll see a bunch of NaNs for not a number. So that's not necessarily a great thing. It's going to do something, but it's going to give us all sorts of not good results. If we run the Logit safe function, it just gives us an error and says, you can't do this, which in some cases can be a useful thing. But if you give it values that are within the proper range, Logit safe will give you the Logit transformed values. So just a nice example of using both conditional logic gates and using and specifying a more complicated function. So one point here is that when we use the conditional logic gates that we've been talking about, if, else, if true, do something, a is equal to 1, else a is equal to 2, something like that. I could run that, and it specifies in this case a is equal to 1 because this, by definition, I've hard coded this to be true. Now, that type of if then else will only work on a single test. So if there's more than one test, it's not really going to work the way we want it to. So imagine we had a true and a false together. What's it going to do? It doesn't know what to do. R's base if then else is just going to work on one test at a time. So let's imagine, a similar set up a vector x that has value, 0 and 1, for instance, and we can say if x equals 1, then we're going to say detected, print detected, otherwise print not detected. And if x has two values, like 0 and 1, R doesn't know what to do. This is a common task, though. Like, we want to potentially perform multiple tests, and for every one of those tests, we will do something if the test is true and do another thing if the test is false. So R has another conditional logical function that helps us in this case, and it's called if-else. All right. So what the if-else is going to do is it's going to take a vector, and for every one of those vector elements, it's going to perform a test, and it's going to return one thing if true and another thing if false. So let's continue the wildlife monitoring example that we've been working through, but this time we're not just monitoring, or we're not just simulating detections and non-detections for one individual. We'll do it for lots of individuals, say 100 individuals in this case. So we'll set this n samples to be 100, and we're going to set the seed, which means, when we use random number generators, it's going to allow the random number generator to give the same number every time. So this is just a way to help when you're coding with random numbers. It allows random number generators to give the same result every time. If you set the seed right before calling a random number generator, it'll always give the same result as long as you set the seed with the same number. Because these random number generators are actually pseudo-random number generators, they actually are generated from an algorithm, and you can kind of trick the algorithm into being deterministic if you give it a seed that is the same number every time. It becomes deterministic. So we're going to set the seed, and now we're going to take 100 random binomial draws, and each time it can either be 0 or 1, and the probability is going to be 0.7 still. So we'll get 100 values that are either 0 or 1, indicating non-detection or detection. So we could imagine this could be 100 visits to a survey site, and we're just keeping track of one individual, or this could be a single visit to a survey site, and we have 100 individuals, and we didn't detect this one, we did detect this one. So however you want to think about it is fine, but we're just going to think of this as non-detection and detection. And all right, so if we wanted to kind of report back, we like whether there was a detection or not detection for every one of these elements, you could not use this syntax. So y, since y is a vector, R is not going to allow performing multiple tests. So we've already seen that, but we can use if else to accomplish that task. So in this case, we're going to say if else. We'll first implement this test if y is equal to 1, and that evaluates to a whole bunch of trues and falses. For the trues, we're going to print detected, and for the falses, so the trues come first. This is what we do if the test comes out true, and this is what we do if the test comes out false. And if we run that whole line, that's what we get. So for all the trues, it's going to print detected. For all the falses, it's going to print not detected. And we can store that as an object called detection history, and we get this vector. All right. And we can go the other direction too. So we could take that vector of detection history, which is just, detected and not detected, and perform another test. Is that value equal to the string detected? If so, it's true. Otherwise, it's false. If it's true, we replace that with a 1. If false, we replace with a 0. and we can perform that test, and we get that vector of zeros and ones back. Because we set the random seed, you should have the same results as I do. Even though it's a random number, you should get exactly this sequence of zeros and ones. That's what setting the seed does. It just makes it repeatable. It essentially makes random number generators repeatable across different computers. You should get the same results as I get. And finally, I just want to show a slightly more complex example, again using the if-else function. So first, we're going to make a matrix using the cbind function. So we're just going to combine two surveys, for instance. And so the first, you can imagine this is like day 1 of a survey, and this second column is going to be day 2 of the survey. So remember, cbind just combines two vectors and puts them side by side as columns in a matrix. So we're going to have a vector of zeros and ones of length 10, and then a vector of zeros and ones of length 10, but this time the probability is a little higher. And we're just going to put them together side by side as two columns using cbind, and then store it as an object called xt. And so now we have this object stored. And now we're going to do another test. This time we're going to go across all the columns here, column 1 and column 2. And if the individual is detected twice in both surveys, for instance, we're going to say detected twice. And if it's not detected twice, if there's at least one 0 or non-detection event, we're going to say not detected twice. So we're going to use the AND Boolean logical test, and we're going to combine, this test, which is, going element by element down the first column and asking, is it above 0? So trues and falses for that. If it's 1, it's going to be true. If it's 0, it's going to be false. And do the same thing for the second column. And we're going to combine those by saying, if this is true and this is true, we're going to get another vector of trues and falses and this time the trues represent both columns being 1. If that's true, we're going to print detected twice. If it's false, we're going to print not detected twice. So we can run that, and that's what we get. So take a minute maybe to make sure you understand conditional logic and make sure you understand function specification. We're going to end this video now, and we'll pick up with for loops and other types of iteration operations in R in the next video.